Hey, 6:01. Let's get started. I hope I started recording. Yeah, I started recording. So today we are supposed to review on these lectures 8, I guess. Memory usage 2. So is there any question now on that part? I see there are some on the discussion. I'll come to that. But on a live, if you want to ask me. Okay, all right. So let's look at this discussion question first, and let me try to answer. Let me share. All right. So I have this one. Let me reply onto that. I don't know. I'll find out. I just need some time to research on that. Okay, so hold on to that. That's an interesting question, but I don't know yet. And next, can you explain the system size limit of maximum amount of memory? For instance, why the maximum memory is 4 GB considering the 32-bit GB? And also, can you explain how the addressability affects the maximum memory size? Okay, this is good question. This is good question. Let me try to explain this one. How do I want to explain it? Okay, maybe we can use the Jamboard to do that. I think that's the two questions I have. Okay, so let me stop sharing and share my Jamboard. Yep. Share. Okay. So so first question is why this 32-bit system maximum memory size is 4 GB, right? So in a 32-bit system, your processor is processing like 32-bit, can process 32-bit at max, right? That means, let's say this is my processor, microprocessor. That means in it can issue an internal it can issue an address, which is an address, and which is being driven probably by some internal register. We don't know, some register is driven by that. So being a 32-bit processor, this one, the size of this internal register driving the address is also 32 bits, right? So this is also 32 bit, which is making this address line as a 32 bit. Now at the memory side, so you are receiving an address of 32 bit. That means number of storage is 2 to the power 32, right? Maximum means, what does it mean maximum of 2 to the power 32? Means that this processor, 32-bit, can access these many addresses. Even if like it has, this memory is offering more than that, it can still access only 2 to the power 32 different unique addresses. Now, that means if each storage, or sometimes we refer it like just in commonly as each address, can store 1 byte, then this microprocessor can access 2 to the power 32 byte of data at max, and that is being really limited by this 2 to the power 32, which is being really limited by this 32 address bits, which is really limited by this amount that processor can process through the registers, is a 32-bit for 32-bit processor. So that means this is equals to 2 to the power 4 into 2 to the power 30 bytes. This is equal to 4, and this is unit is gigabyte. So that's why we have a limitation that a 32-bit processor can access max 4 gigabyte. Carter, is that like sounds good?
Yeah, that cleared it up very well. But so say this was word addressable memory, it would essentially keep track of 2 to the 32nd words.
Exactly. Now let's come to your other question. Like we assume this is a byte addressable memory, and that means each address has 1 byte, and which is usually the case for the processor to think about the memory. So I'm putting it in a little bit convoluted way, that the processor thinks the memory is a byte addressable, and it sees that each of the address is 1 byte. But in case we change that assumption to make it an word addressable, each one is a word, right? That means in our calculation, we are going to make it a word. That means we are going to make it a 232 words, which is like word. A word is a 4 byte, right? Yeah, word is a 4 byte. So that means it's going to be 16 gigabyte. Word equal to 4 byte. So it really depends on the addressability of the memory of the system. Addressability of the memory of the system. Now I want to make sure you understand this part well. So addressability of the memory is one word. That really means my processor is thinking that this memory per address is storing 1 word. So it is definitely always, for a byte addressable or not, it always return or extends data by 32-bit, right? By 32-bit. Now the question becomes, if the processor is assuming each address is storing 1 word or not, because you'll see in the next lecture, memory is really as a device is really a word addressable device. But since processor thinks it's a byte addressable, it actually raises an issue called alignment, data alignment issue. That will be in the next lecture, like this memory usage of 3. So all this addressability perspective, this statement is all coming from the microprocessor standpoint, that microprocessor viewpoint. That microprocessor is thinking that my memory device is byte addressable or memory device is word addressable. It's not really depending on the physical device or what we are putting there in the like motherboard as example.
Professor, actually, I want to make sure when we say that, for example, this memory of the computer has a 16 gigabytes, it means that the word, not the byte. You mean this one? For the capacity as whole memory is 16 gigabytes. Okay, you're talking about the word. I didn't get about the word. You said that 1 byte, 1 word.
Yeah, like, okay, so 16 gigabyte. So nowadays 16 gigabyte is very common, right? Very common.
Yeah.
Your laptops and desktop probably has more than that one, right?
Yeah.
So can we say this is a word addressable? No, we cannot say it. This addressability all is a perspective of your processor, what your processor is thinking, okay? And in usual model, it actually byte addressable always, 16 gigabyte or 4 gigabyte, doesn't matter. Now the point here is that this, if you are seeing a 16 gigabyte of memory in your system, your system itself is possibly 64-bit processor. Because for a 32-bit processor, you can access maximum of 4 gigabyte. You cannot go beyond 4 gigabyte. So that's why you will see, like in your old system, if you have old system, you cannot put more than 4 gigabyte on those machines.
Professor, what is the maximum memory that a processor can access with 64 bits?
That's an interesting question, right? Theoretically, it access. Okay, let me go to the next. Oh, I don't have the next one. Okay, so let's talk about this 64-bit. So that's a good question, and we need to discuss a little bit on that one. Interesting one. Okay, clear the frame. So on a 64-bit machine now, with that same understanding, on a 64-bit machine, you have this microprocessor which is address is, let's say, 64, okay? And it's a byte addressable memory. So that means, so this is my memory. That means I have these 2 to the power 64 addresses, and each address holds a byte. That's from your processor viewpoint, okay? It really doesn't matter what the memory device itself is storing or not. It's completely from viewpoint of your microprocessor. So that means size is 2 to the power 64 byte, 2 to the power 4, 2 to the power 30, 2 to the power 30 byte, which is like it's 16, and this is 2 to the power 30 gigabyte, I don't know what is the gig of gigabyte, but it's a really, really big number. Really, really big number. However, there is an interesting twist. If you open up any 64-bit machine, you see on the motherboard, like you will see there are only 40 lines are connected to the memory. Usually, like so far the systems supports that way. So that means processor actually are not using the full address spaces. One reason is that this 16 into 2 to the power 30 gigabyte is a huge number. No memory device can support it, this big storage. Okay, so what it stored then as a physical memory, it's a 40-bit is used as an address. So that means 2 to the power 40, that is your limitation for your 64-bit machine right now, as of now, from the hardware perspective, how the connection are made to the memory, and that many bytes, which is like 1 terabyte basically. So you can have max memory of that 1 terabyte at present. Okay, of course, like in future it can go up to like another 2 bit added to that, 4 bit. We have space. As the memory technology goes like advances, we can possibly place more and more memories onto the systems. But itself 1 terabyte is a huge main memory size perspective. Like I don't know, I don't remember if any system I have seen with the 1 terabyte of main memory. Yeah.
So is this kind of, I guess, similar to how IO mapped IO works, since you have separate lines for memory and separate lines for everything else?
These are all memory mapped IO. Like no modern system uses IO map IO usually.
Oh, so those 2 to the 40, those 40 address lines also include all the IO.
Yeah, all the IOs. Yeah, all the IOs. Yes. So here, one interesting fact I want to share with you, in advanced programming, what we follow sometimes, let's say we want to compact our memory usage footprint. Okay, we want to use less amount of memory. And let's say we in the object address spaces, we use lot of addresses, sort of like at the C level. I don't know if you have, how many of you have programmed with C, but if you have programmed with C, which is a very powerful language, much more powerful than Java, by the way, but it's also hard to use. It supports the pointers. It supports the pointers, and that pointers in 64-bit system or has to be a 64-bit. And now you see that in physical reality, it is using 40 bits. So it is using 40 bits for your address, and rest of 24 bits are unused. So we can really use this 24 bits to store different other information. Okay, and that's what we follow. If we really go into the memory crunch, that we want to reduce the memory consumption by the application, we actually go with this strategy, use these unused bits in the program, in the memory addresses, to store or piggyback some other information onto it and use them. So that's one interesting things actually we do in the industry, enterprise level programming.
So, Professor, 40 is something like what every processor would use. I like since most computers only have like 16 or 32 gigabytes, so we don't really need 40 bits as well, right?
Yeah, that's true. But at the system level, they wanted to make it 40 bit in the hope that memory industry will catch up one day, and we can use 1 terabyte of primary memory in a system.
Okay.
let's see how long it will take to go there from today's technology.
Is it not possible to use SSDs as memory?
Uh, that will actually diminish the purpose because SSD is much slower device than the main memory, that technology, DRAM technologies and other stuff. So it will slow down your system. So your return on investment won't be much if you want to use SSD kind of technology, like a flash memory in general, as a primary memory. That will slow down your process, like whole system.
Professor, is it true that there exists some SSDs that can go directly on PCI slots where the
There may
graphic
be,
cards go?
yeah, there may be, yeah, definitely.
Okay.
Like especially like a part of the memory is a read-only part, right? And in older technology, it used to be like this once written this very hard-coded device which used to be placed on the motherboard and which can never be overridden and stuff like that. And there comes another type of read-only memories called programmable read-only memories, which can program once. We can place some information in that part, and then it become read-only. So from that, it's kind of placing the SSD as a part of the memory, the part which needs to be like an permanent basis. It makes sense because it's flexible. You can change the content there, especially if you are upgrading the firmware or stuff like that, which is like resides in between operating system and the hardware, bare minimum hardware, the firmware. They all basically goes into this SSD and they act as a part of the memory. But remember that part is accessed very like sporadic way, like maybe at the beginning of when you switch on the system, only that part, it basically access that part. Every other part is basically accessing this DRAM, the high-speed memories. So that's why like you cannot just replace the every DRAM with an SSD. It will slow down the whole system.
So to the day, the fastest RAMs are only DDR4 RAMs, right?
Yeah, I think so. Yeah, I haven't been looking at those components for a long time, but I think so. Yeah. Maybe you want to look up and search in Google and see what are the fastest RAM available in the market. Like different companies claim different data and they have the published information there. Yeah.
Professor, what does it mean by byte addressable memory?
So byte addressable memory means that processor thinks that each address contains 1 byte.
I see, thank you.
Okay, what else shall we do? Let's see. Memory usage 2. Okay. Why don't we have that class poll of preparedness? Let me see. Okay. Okay, I'm launching the poll for a minute and let's see how much prepared you are today for this class. Okay, we have 41 of 41. under appointment. Okay, end polling. Let's see. Let me share the result of the polling. About the lecture videos, about 40% watched all of the lecture videos for today. That's good. 49%, almost 50% have read the topics. That's also good. 12% has some questions. Yeah, we have some good question. Yeah, 61% do not have any question. That's worrying me, especially looking at that these slides of these lecture 8 memory usage 2. I thought you'd have some question about these slide 5 and 6, that dangerously looking expressions there. Don't you guys have any question on that? Okay, I'll share what I mean by that. Okay, screen one, share. Which one I'm sharing? Hey, screen one, share. Okay, what I mean, this one, right? So everybody are comfortable with this?
No, it's so hard.
How come I don't have a question?
Professor, actually, I don't know when should we use these ones. For example, I know that it's for example, to load values to register from memory, or memory from to the register, but I don't know how to use it and when should I use it on a Mars, for example, ID.
Okay, all right. So let's do one thing. Let's do a problem, okay? Let's do a problem. Let's see if I can copy paste from my note. And this also has this, this lecture has this thing, your Indianness. Remember Indianness? I was expecting some question from the Indianness. But let's see this problem, right? This problem says that 32-bit system has a main memory, which is byte addressable, content from this address, an address in the increasing order. So the content is this, like we are starting from 400100EE. What would be the value loaded in the T0 register with instruction load word T00S0, something like that. Or you can assume like in the MIPS way, T0S0, 0. Let's say. Assume that S0 is this, S0 content is this, okay? And then what would be that loaded value into T0 if the system is a big endian system or system is a little endian system. So that's the problem statement. And I will, okay, there is a question from Christopher from, is there a new Jamboard? No, it is not. It is on the page 2 because apparently Google don't want us to create more than 20 pages on the Jamboard or 20 Jamboard. So I'm recycling the previous one. I'm started from 1 and then coming to the 2. Yeah. So, so at this point, I would open the breakout rooms. What is the time? 6:30. Yeah, for 10 minutes. Okay. And this is your study group. Discuss this problem among yourself. Okay. And see how you can solve this problem. Then we'll be back. Okay, let other just come back from the breakout room in a second. And which room wants to go for an explanation? Jeffrey, are you, you're on mute if you're trying to say something.
No, I wasn't saying anything.
Oh, okay. So any room has done this problem, or anyway, haven't even, you don't have to be done with the problem, just if you want to share your ideas what to do. In this case, we can probably look at your Google Doc and share with everyone. Okay, apparently everyone is clueless, seems like. So let me try to solve that problem, okay, for you. So share screen, screen one, share, okay. And okay, so this problem, first of all, we need to see how this memory is laid out, right, in that address. So quick way to do that is, we know that our start address is this one, right? Start address is this one. And when multi-byte data, like in this case, we have multiple bytes, these multi-byte data are written or stored into the memory, they always goes with the increasing order, increasing order. So that means if I want to draw this memory content at this point, let's draw that memory. So how many data I have? 1, 2, 3, 4, 5, 6, 7, 8. Okay, not bad. This is a piece of memory. And we have, so I tend to write it from down to up. Lower address goes at the bottom and upper address goes at the top. So that is my convention. You can go in other convention, that's okay. Like, it really does not change the result or outcome. 0, 0, EE. That means next would be 4, 0, 0, 1, 0, 0, E, F. Next location would be 4, 0, 0, 1, 0, 0, F, 0. Is it? EF plus 1, 0, and E equals to F. Okay. The next one would be 0, 0, 1, 0, 0, F1. Next one, 4, 0, 0, 1, 0, 0, F2. Next one, 4, 0, 0, 1, 0, 0, F3. 4, 0, 0, 1, 0, 0, F4. 4, 0, 0, 1, 0, 0, F5. Now we have these bytes starting from this address, right? So we just note down the bytes there. 2, 3, A5, C7, 9A, 0, BC, 087, 05D, 068. Okay, so this will be how it is stored. Okay, now on to the next problem, or the problem in hand. what it is saying that I want to see what this statement will load in T0, right? This statement is something like I'm loading from some address on the T0, and there comes this scary looking statement, okay? So what it is telling really that our register R of this RT, that means our T0 register, is equal to memory. So we'll be reading from a memory, from an address, okay, from an address. So this address is, you take the content, okay, let me just write it in a different ink. Content from the S0 plus sign extended immediate. The sign extended immediate of 0. It's a sign extended of the immediate function, sign extension of the immediate. Actually, I didn't need to write this thing. Sign extended immediate value of the 0. That's what that part means, okay? So this is more like your address calculation, what address you are calculating. Address calculation. So at this point, you are seeing that given that S0 has this data, right? So it has 0 cross 4001 00F0 plus sign extension immediate value is 0. So this is not a challenging problem at all. It would be challenging if I would give some, like maybe some hex number there, like F.
Excuse me, Professor. I think your
Yes.
screen is a little messed up. I can't
Oh.
see what you're doing.
Oh, sorry. So
Thank
what
you.
I was saying that this part is like coming from the S0 sign extension 0, and S0 is given at this address with the sign extension 0 is 0. But it would be an interesting problem if something like I give something like this 0FFFF8. So this is a 16-bit negative number from 2's complement perspective. So you need to figure out what that complement number is, what is that negative value is, and maybe it becomes like minus 18, something like that. So you need to add minus 18 on top of that. But that is not a problem now. Our problem is simple. Okay, our problem is simple. Oops, I lost my Jambo. Just hold on.
So, Professor, in this case, is the sign extension 0 because the register S0 contains a 16-bit number? I'm sorry, not a 16-bit, a full word.
Yeah. A complete word, 32-bit. Yeah.
Right.
And sign extension 0 is basically 0. Okay. So your address in this problem is basically this, right? Basically this value. And what is that address? Here. Now you are accessing from this address, and again, memory address reading is always for multi-byte reading, like the load word is a multi-byte reading, right? So it will go from lower address to the higher address. And load word is a complete word, so we need to read like 4 byte out of this, right? We need to read this address, next address, next address, and next address. right? We need to read them, these four. And now question become, what would be if the system is following big endian system? So big endian system assumes your lower address contains the MSB. So that means in this case, it will be 0C79AB87. That's for the big endian system. And for the little endian system, that assumes that your lower address contains the LSB. That means highest most address contains your MSB. So you need to write down in that order 087BC9AC7. That would be your little endian system. We load with this specific instruction. Question so far?
Professor, for the sign extension, are the zeros padded on the right-hand side?
Sign extension, okay, I'll come to that. Okay, sign extension is not zero padding. Okay, it's something else. Okay, what it is basically, let's see. Okay, sign extension is this. Let's talk about the sign extension. Okay. Let's say let's start with the smaller bits. Okay, let's say 4 bit. So 4 bit can represent from -8 to 7. That is the range, right? And let's say 4 bit, okay, definitely I need to specify 2's complement here. Complement. Now that means a bit pattern like 1101 is basically representing a negative -3, right? Am I correct? Can someone confirm this? 1101, 4 bit 2's complement, 8 minus, this is 4 plus 1, 5, which is -3. I think that's the one. Okay. Now I want to extend this pattern or this value to the 8 bit 2's complement. Now what that bit pattern would be? It will be like 1, 1, 1, 1, 1, sorry, 1, 0, 1. That is -3 in decimal. Now take one more example, which is 0, 1, 0, 1 in base 2. In this 4 bit 2's complement is practically 5 of base 10, positive value of 5. So with the 8 bit 2's complement, it will be 0, 0, 0, 0, 0, 0, 1, 0, 1. That is 5. Right? Now observe that for a negative value, we basically replicated this MSB, right? And for the positive value, we basically replicated its MSB, right? So we are replicating the MSB side, MSB of the 4 bit pattern into another 4 bit to make it a 8 bit 2's complement representation. So sign extension is this. Okay. Now what is my, okay, question so far on the sign extension? Then I'll move
I have a question.
Yeah.
So in the lecture, there was like, I guess you can add a value or subtract a value from the GP register's value to get to the different memory addresses. So I guess in that case, they're using unsigned numbers.
No, they uses the offset values in the lecture. This one, like a load word, this instruction you mean? This offset.
Except like you can have like a plus FFFF and then like $GP.
FFFF $GP. Or with respect to the global pointer, you are you are still bound with this number, right? This is like a negative side. You have some you have some range of the 16-bit signed representation, 2's complement representation. Just like 4-bit has like a range of -8 to 7, so 16-bit 2's complement will have some range, right? So GP, using this as a base register, you can go either higher addresses, you add positive offset, or you go lower addresses with the negative offset, right? Lower addresses to the negative offset, and that gives you the entire range of numbers or addresses that you can expect or access from the global pointer, from using global pointer at your base register. So this is like 64K locations up and down together.
Oh, so that's completely different from sign extension.
No, it basically depends on the sign extension, right? It is this offset is computed by sign extension anyway. So you are using GP here, global pointer in this register. Okay, so instead of like using a S0 as a base register, you will be using $GP here. Now question becomes how much offset from that global pointer values you can make, which is a 16-bit 2's complement range, right? Which is like 2 to the power minus 2 to the power 15 to 2 to the power 15 minus 1. So that would become your range of the offset value, and that the address ranges you can operate on with using the global pointer. So they're related.
I think later on in the lecture slides, there are like examples where there are unsigned values, I suppose.
This one?
Yeah, or I guess not 2's complement, but like the plus and minus.
Yeah, this one, so that's one what I, if you look at the video once more, you'll see these are like what I wanted to demonstrate is this. This is not a basic instruction anymore. You will see this instruction is replaced by the assembler treating this guy as a pseudo instruction with multiple steps.
Oh, so the basic instruction is what was shown in the Jamboard.
Yes, basic instruction, as long as this offset value is within 16-bit range, it's fine. Okay.
Okay, thanks.
So as soon as you go beyond that 16-bit offset range, assembler treats that as a pseudo instruction and replace that with the two instruction, I believe. Like it basically involve AT to add some values and so on and so forth. So try it in the Mars and look at what instruction it changed. But they are pseudo instruction. They become pseudo instruction. Okay, is that?
Yeah, that explains it.
Okay. So let's get back to our discussion once more here. So what is going on now? Now think. Okay. Now let's go back to the zero extension. There is something called a zero extension. So zero extension is the one that someone has just asked me. Is it padded with zero? Yeah, that is called a zero extension. So 0 extension of 1101 base 2 is basically like from here, we're going to 00001101 base 2, right? And for value 01012, 0 extension is 0000101 base 2. So now you see, like, let's say it was an 4-bit 2's complement, and it is 8-bit 2's complement. Then actually we are messing up with the value, right? This guy was -3, this guy was +5, and in this world, this is +5, this is +5. That didn't change the value. But this guy is now 1230. This guy is +30. So this definitely messed up with the value represented by 4-bit versus 0 extension. So if you are dealing with the real value like offset and all this stuff, we should always do a sign extension. We should always do a sign extension. But when do we then need the 0 extension? Is for the logic operations. For example, if you are dealing with something like or I, $0, $S0, some 16-bit 1 to AB, some bit pattern. In this case, you definitely don't want to do a sign extension. This will be 0 extension because it's a dealing with a logic. So that's what assembler does. It actually extends this bit pattern with a 0 extension for a logic operation. But in the same case, if you do an add I, $0, $T0, S0, 1 to AB, assembler will do a sign extension in this case, because we are dealing with an arithmetic function. Make sense?
That bottom line was blocked by the,
Come again, sorry?
we couldn't see the bottom line there.
Now you see? So for the add I, assembler will treat this bit pattern with a sign extension. It will not 0 extension. But the logical operations like or I, it will do a 0 extension. So 0 extension is useful, even though it can change the meaning of the value, but it is needed for the logic operations. Question? Okay, so with that, now we understand this part. Now the other part is something like these operations, like 16-bit 0 of this thing. Okay, so what does it mean? So it is a load half word, okay, with an immediate value and some base register. So memory address is the same thing. We are reading from that memory. We are reading from the memory. We are calculating the address in the same way. We are sign extending the immediate value, etc. But what we are doing in the load half word instruction is that we are picking up the lower 16-bit and upper 16-bit is padded with 0. This is the meaning of that. 16-bit of 0 I am putting in the higher part of the 32-bit, and whatever I am reading from the memory, that 32-bit, I am throwing off the higher 16-bit, and I'm only appending the lower 16-bit into my incoming bit pattern, and that's the value, that's the bit pattern will be loaded in my target register. On extension to that, load byte unsigned, what it will do, it will basically pick up the lower 8-bit from the whatever data, 32-bit data you are reading from the memory, lower 8-bit and upper 24-bit will be replaced by 0. That's the load byte unsigned. Whereas signed half-word loading and signed byte loading is more towards this thing, like it's basically doing a sign extension of that. Okay, so what it means really is you take a 16-bit, you replicate the MSB of the 16-bit pattern, right? So you're reading from the memory, From that memory, you pick up the 16th bit and replicate it. So it is same as like your sign extension. You're picking up the MSB of the value you are looking for and replicating that many times, right? So that's what it is doing. You are picking up the 16-bit from the memory read of 32-bit, replicating that 16 times, and concatenating the lower half, lower 16-bit on top of that to make that whole 32-bit pattern. On the same note, load byte is the same way, is a 24-bit concatenation, but we are replicating the 8th bit of the incoming 32-bit data, replicating it for 24 times, and then concatenated with the lower 8 bits on that. That's the load byte pattern loads into the register. Question. Okay, so one more thing I want to discuss with you before I let you go is this about this endianness. Let me clear this. Okay. So sometimes, like, let's say there is an like this ASCII Z and hello world. Let's say we are defining a string there. And let's say it is starting from a memory location of, I don't know, let's say 1001000. So this becomes like 100100001, 02, 03, 04, 05, etc. Right? Now, question is like, let's say this string is placed from this address. So what will be content in a big endian system versus little endian system when it is dealing with laying down a string? Answer is no difference. Why? Because endianness is applied to the multi-byte data, like a word, like a half word or double word. For a byte, it can place anywhere and it doesn't really follow anything. It doesn't need to follow any endianness there. And strings are nothing but like series of bytes, right? This is same as bytes like ASCII for H. I don't know what is the ASCII like. ASCII for H, ASCII for E, ASCII for L, and so on and so forth. So really, it doesn't matter what endianness is this. It will still lay down the ASCII code for H here, here L, L, O. This is blank. Then hello world, WORLD, playing, etc. Okay, so it really doesn't matter whether it is a big endian or little endian on a string laying down. This is sometimes confused. I have seen in a past semester confused student a lot. Like they think like a big endian will actually do this way and little endian will do this way. HELLO blank WR world playing. No, this is wrong because this is just a byte data, nothing to do with a multi-byte endianness. Question? All right, if you don't have any more questions, then I will end today a little early. Remember, you have the programming assignment 2 tonight and programming assignment 3 on Wednesday. All right, see you on Wednesday then.
Thank you, Professor.
Thank you.